Okay, guys, let's continue with another type of linear data structure. This is DAX, and as opposed to queue or stacks this time, it's double-ended, which means that we can do operations from the front and from the back side. I can add some items to the front, remove items from the front side, or add items from the back side, or remove items from the rear end of the, let's say, data structure. And it's a very nice property, a kind of a hybrid data structure having the properties of queue and stack. So we don't have any restriction on the adding and removing items. These are things I mentioned. Very similar. It has some similarity with stacks and queues, but combines the advantages of these two data structures. So we cannot say that this is an last in first out or first in first out type of data structure. It's an hybrid. We don't have a specific name, a short name for the explanation of this data structure. Again, we have similar operations this time. We have some 2 add operations and 2 removing operations, but the rest is the same. We create this data structure by a DAC operation. We check the DAC whether it's empty or not and calculate the size of it by using probably a length kind of function in Python implementation. Now let's have a look at add operations. We are adding an item to the front or adding an item to the rear end of this linear data structure. We have the same ones for the remove operations. We can remove from the front or from the rear end of this data structure. And we have the same example once again, but obviously we have different operations. We first create a data structure DAC with the help of this operation D, and at the beginning, since we didn't add any value, it's an empty, and once we check, once we use or run its empty function, it will return you a true value. And if you start adding items, but this time, as you see, we have 2 different operations. We are adding item to the rear. This is 4. And once we add dog, as you see now, that will be the content of our DAC data structure. We now continue adding item from the front. But this time, cat will be in front of the 4, which was the first item in our DAC data structure. And then we continue with the same operation, adding item to the front, and true will be in front of cat. So at the front, we have true value, and at the end of the data structure, we have a string called dog. And once we check the size, it will return you a value of 4. Obviously, this is not empty. We have 4 values inside, so the returned value is false. And now we have another adding item operation. This time we are adding the item from the rear end. So 8.4 will be added from the back side. And now we have 2 removing operations. We are removing item from the rear. So the item at the left-hand side or at the back of the data structure is 8.4. So once you call it, 8.4 will be removed. And once you call the same operation, we will be removing, not the same, I'm sorry, but this time removing the item at the front of the data structure. And true was at the top or at the front of the data structure, so it will be removed. And now we have just 3 items left in the DAC data structure. So this is a simple implementation, and you will see that it's a hybrid implementation of queue and stack. As always, we are creating an empty list. And then for checking emptiness, it's not that difficult. Size is again the same, but in between we have adding and removing operation. Adding front is very similar to adding items in the stack. We simply append it. But if you want to add an item to the rear end of the data structure, then we should follow a similar rule as it is for the Q data structure. Now, if you want to remove from the front side, this is simply done with the help of the pop operation. But if you want to remove an item, this is the first time actually we are using such an operation, such an implementation, let's say. This time we will be popping the item with an index of 0. But if you have an empty pop operation, it will always pop the topmost item or the item at the front of the data structure. But once you write a specific value here, like here is 0, if it's 0, then that means the rear end of this data structure will be removed. Any questions, guys, about the implementation of DAG data structures? Okay, so where can we use actually these DAG data structures? It's not very common, but there might be some specific problems where using such a data structure is highly appropriate. So you should remember to use DAG in such cases. What are they? An example, the first example is a palindrome checker. What's the palindrome? It's a word actually having the same letters at the front and at the back, we can say, at the end of the word. So if you look at this word level, we have a letter L at the front and at the back. And once you remove them, again, we will have the same letters at the front and at the back. And these are some other examples. I, race car. So how we can use the DAG data structure? We may have a specific algorithms, and we can put these, actually split this word into letters, put all the letters into the DAG data structure, and then while removing items from this DAG, we can check their content. If they match, then that means it's fine. We can continue checking operation. And if you just have a single letter remaining, then you can easily say that, yes, this is a palindrome, and you can stop checking the operations. So that's it, actually is an example. We add all the letters into our DAG data structure, and then what we do, we remove one item from the rear, one item from the front side, and check whether these two letters are the same. If they are the same, you should continue removing items, but if they're not the same, then you should break at that point, stop the operation, and tell the user that the given word is not a palindrome. But if there is no problem, if the letters are matching, you should continue until you are left with a single letter in your DAG data structure. In our case, we will be just having a letter D, and at that point, we should stop and tell the user that this word rather is a palindrome. This is the implementation. We import the DAG class, and then this is our definition for checking whether the given string, whether the given word is a palindrome or not. So what we do, we first create a DAG data structure, character DAG. So for each character in our string, what we do, we add them to our DAG data structure. This time we are adding them from the rear, but it's not important. You can also add them from the front. It should be the same. And we have a variable. Initially, this variable is true. We are assuming that the given word is true, but during our checking operations, we may come up with a conclusion that this should be false. So let's continue the checking operation here. If the DAG size is higher than 1 and the still equal value is true, which means that during your checking operations, if you have more than one letter, and if you are still knowing that this might be an palindrome, then you should follow these expressions. What are they? You should find the first letter, the last letter. We find them by using removing operations, but for the first one, it will be remove front, and for the last one, it's obviously remove rear. And then simply we check the first and the last items. If they are not equal to each other, then we can say that this is false. So this is not a palindrome, and we should stop the operation. Since if this is false, once you go to the start of this while loop, you will see that this condition will not be satisfied. Since it's an AND operator here, this is okay, but if still equal is a false one, then we cannot go into this while loop, and we should continue and return this result. If it was a false one, it will simply say that the given string or given word is not a palindrome. But if it's true, you should continue these operations, and if still you satisfy this condition, then you may say that the given string or the word is an palindrome. Any questions? So now I will talk about the list data structure, which is very similar to the main data structure in Python programming language. But here in this part, we will be talking about lists in general. So we will be just giving you the fundamentals of list data structures. Some issues might not be exactly the same as the list data structure in Python. So please keep it in mind. We are talking in general about the list data structures, since you may also have a kind of a list in C++ or other programming language. You need to create these data structures. But it's already created in Python. You don't need to spend more time. There are some little differences, but you can handle most of the operations with the help of the nature data structure of Python. And I can say that it's a very powerful data structure. If you remember from the previous data structures, we constructed them by using the list data structure of Python. So they're flexible. You can do many operations on them and create new data structures. And obviously, and some of them has built-in list data structures, some programming language, but some does not. So in the list, actually, we have a collection of items. We have many, let's say, sometimes strings, sometimes numbers. It's up to your problem, up to your implementation. Another important issue in the list is that the values usually have a relative position. So their orders sometimes becomes important. And once you have ordered lists, some operations will take less time. But if you have unordered, if you put items randomly into your list data structure, then some operations, let's say like search operation, will take more time. Another thing, we are assuming that we don't have duplicate items in our list. Each item is unique, and we don't have another item having the same value in the given list. Here's an example. For instance, we have some collection. We have a collection of integers: 54, 26, 93, 17, 77, and 31. And this is an unordered list. We can easily generate in Python by using such an expression. But as you see, we don't have an order, ascending or descending, but we don't have such orders in this unordered list. So how do we implement such unordered list? What type of operations actually should we have in this data structure? Again, we need to create a list data structure. We need to have some operations for adding and for removing. And sometimes this search is quite useful since you might have, let's say, thousands of items in your list, and search becomes highly useful if you are looking for a specific value. And then we have isEmpty or size operations, very similar to the previous data structures. We have append item. We are simply adding this item to the end of the data structure. The index operation will give us the index of a specific item. And it's very similar to search. So in index, you should first do the search and then return the value of the index. We have some other operations in this unordered list data structure. The first one is here, insert on the right-hand side, insert operation. You need to define the position, the index of adding a specific item. And this is the index, and obviously with the item, you give the value in the pop operation. You simply remove the topmost item from the data structure, or if you want to remove a specific item, specific position index, let's say, you need to give this to this pop operation. So how we do the implementation? We need to have a kind of a relative positioning between these items. And this should be maintained somehow so that while performing all these operations, their order will not be modified and we will have the same fashion. Another issue is that you don't need to actually reserve a continuous memory. Assume that this is your RAM block, okay? Random access memory block. Yes. You have such, let's say, slots, memory addresses for your values. Obviously, it will be much easier if you have a continuous memory, but that's not a must. We may have, let's say, the first item here in your RAM block and the second one maybe here. So you need to have a kind of a connection between the first value in your unordered list and the second value. And then the third item might be here. So you need to somehow have a kind of an directing information in the second value to the third value. So this is another illustration. We need to have a head, but obviously in the head we don't have any value. It's just directing the address of the initial value, which is 54 in our example, and then 54 should direct us to 26, then to 93, to 17, to 77 and 31. And at the 31, we should know that this is the end of the list. Since while running the length or the size functions, while we are going through all these values, we need to stop at some point. And with a kind of a specific operator here, we will know that this is the end of the list and we should return the number of values in this list to the user. Another important, once again, I want to repeat here, the hats operator here, it doesn't have a value, but it has an address to the first item in our list. And here it is 54. Any questions, guys? I think one of you asked and other guy answered. Thank you. Yes, Ahmed, do you have a question? Okay, no questions. So now, however, I guess let's go into details of the implementation. We need to have a node class, and that will be the basic building block in our implementation. And in that class, we need to have the value of the item, and we need to have a kind of a reference to the next item in our data structure. This is actually, we have a actually some direction from previous value, and the item here is 93. But right now it's connected to the ground, so which means that this is the end part of the data structure. This is actually the end of the data structure. We have a specific illustration here. It's connected to the ground. It's not directing any other value in the list. It's just directing the ground. So which means that it's the end of the list. So this is how we do the implementation while generating the node objects. This is the initialization part, and the given input is directly assigned as a data value, but right now we don't have the address of the next item. Since there's a class right now, so in the initialization we keep it as non-value, but once you assign value, then this next will be changed. And we have some get and set operations here. We get the data with the help of this get operation. We get the address of the next value in our unordered list. This is done with the help of the simple operation here. And then we have the set operation. So for the set data operation, we need to have the value of the new data. And this data is directly assigned to the data variable of our node object. And then we need to assign the next value, the address of the next value, and this is done with set next operation. Once you give the address, it will be assigned to the next variable of our node object. So this is how we start. In the head, as you see, we don't have any value, and it's just directing us to a specific memory location. This is our first value, 54, and then we have an address to the second value. It goes on like this, and at the end, we don't have any reference to a new value. This is directing us to the ground. So this is the end of the unordered list. So this is how we create actually the list. The initial class was about creating just nodes, simple single items, but now this is a class for the whole data structure, unordered list data structure. So what we do in the initialization part, we create the head. This is simply non-value here, and we can check whether this list data structure is empty or not by checking the head value. If the head is actually directing somewhere, then that means yes, we have some values, it's not empty. But if the head value is an empty one, we can say that there is no values in the list data structure. So in the next operation, what we are doing, we are adding some items to this list. So how it is done? We have the value of the item, and then we create a temporary node class, and the data of this node object is equal to the given input item. And then what is the next item in our class? Right now we set it as the self head. Since we have a single item here, we are assuming that this is the next item, and then we assign the head of this item to the temporary value. So this is how we do the add operation. So initially, this was our head. We have just 4 values, and now we are trying to add a new value of 26, and we create such an item that it is a value 26, but it's directing to ground since it's not connected to the list data structure. So what we do first, we first have a connection between the new item and the top of the already available data structure. This is the first step we should do. And then we change the direction of our head to the address of our new item. Since this time 26 will be at the top of our list. So in our new configuration, the head should be heading to the 26. Any questions, guys, about how we do the add operation? Okay, and now we have, if you remember, there were many operations related to the unordered list. We had add, remove, search, insert, pop operations, so that we have many operations, and how we are going to implement them, we will be using a kind of an traversal. In traversal, what we are doing, we are systematically visiting all the nodes and then going sometimes back, or depending on the operation, we may stop at this point and return the result to the user. For instance, this one, the first one is about the size. So how we determine the size of this unordered list data structure? We have the list, actually, this is an input. So right now we assign the head of the list data structure as the current one, and we have a count value of 0. So if the head is equal to a non-value, then this count will not be increased and it will be still 0, and we will return that. The size of that data structure, list data structure, is 0. But if the current value, if the head value is not a empty one, then we will increase the size of our data structure, the length data, the size by 1, and then try to get the next item in our list data structure. And this is done with the help of the get next operation, and that will be the new current value. And if the next item has an, let's say, reference to another one, then again we increase the number by 1. And we do it until we come to the end of the data structure. And if it's the end, then we can simply return this value of count variable. And it will be the size of our unordered list data structure. This is for the search operation. In search, obviously, we need to give the list data structure and the item itself, the item actually we are looking for. So again, we have some initialization. This is the current value. The current value is the head of the data structure, head of the list data structure. And initially, we have a variable of found equal to false. Since right now, we haven't found the item yet, so it's false. And then we start going through the items. If the current actually head is not empty, or if we are not at the end of the data structure, and if the value is still not found, then we do these operations. What we do, we check the data in that specific node. If the value of the node is equal to the searched item, then we can simply say that, okay, we are fine. We have found the value, so make the variable found equal to true and stop the operation. Since if it's true, we'll not be able to go into this while loop once again. But if the value is not equal to item, then what we do, we change the current value. The current node values change with the next item in our list. And then we repeat these operations until we reach to the end, or until we find the item we are looking for. But this is how we do the search. So this is graphical illustration. Right now, this is the current value, and the item we are looking for is 17. So it's not equal to 17. We need to move on. And now the current value is 26 and it's not equal to 17. So we need to get the next item, 93, not equal to 17, move to 17 and assign it to the current value. And right now, the current value is equal to the item we are looking for. So we are stopping at this point. We don't need to go into the deeper of this unordered list data structure. We can stop here and tell the user that there is such an item in your list. Right now, we are not reporting the index, but in other operation, we may have such a feature. Another methods, removing methods, again, is somehow similar, but we need to first find the item we want to remove. So we should follow the fundamentals of search operation and then do some removing and reconnecting operations. So how is the removing operation? So the first and the third statements are the same with the search methods. We have another extra one. It's called previous value. Right now it's equal to none. This part is the same with the search operation. If you find a value, then you are done and you check whether the previous one is equal to none or not. If it's equal to a non-value, then that means you are not actually using to find the value. The previous one is equal to the hat, so we need to get the next one. But if the previous one is not equal to a non-value, which means that it has a kind of a value, then we need to change the connection. As you see here, we make a new connection since we want to remove the item actually we just found a moment ago. So this is for reconnecting the next item with the previous item, but the current item will be removed from the list. This is how we do it. Right now, previous current, and it will be previous item will be connected to the next item. So with the help of this, the item in between the previous and the next items or the current item will be removed from the unordered list. So if the things are actually close to the hat, if the item you are looking is at the head of your, let's say, data structure, then it's very simple, straightforward. You can simply connect your hat to the second value, and the first one will be removed from your list data structure. Any questions, guys, about the unordered list? Now I will talk about the ordered list. There's a question. The role of the previous variables. Do you mean here actually? This is a remove operation. We want to remove, in this example, the item having a value of 17. So we need to first do a search operation. We are searching all the nodes starting from the head, and we find that our item is here, 17. Since it's a removing operation, we want to remove this item. So what we do, we simply disregard this item and try to have a connection between the previous one and the next one. And this is actually done here. Okay. Okay, now we can continue with the ordered list. As the name implies, this time we don't have a random order between the numbers or words. We have a specific order. It might be ascending or descending. It's up to your implementation. And we have mostly similar operations, as in the case of unordered list. We create the list, add item, remove item, search for a specific item, check whether it's empty or not, check the size, get the index of an item, pop an item at the which is at the top, or pop an specific position. So now the search, we will be looking at the search method first. It's somehow similar, but we have an advantage here. Since it's an ordered list, and if you are looking for a specific value, specific, let's say integer value, if you didn't find, and if you find a value which is higher than the value you are looking for, then you shouldn't go on. You should stop right at that point. Since it's an ordered list, you cannot find your smaller value in the higher range. You see now we have an ordered list, 17, 26 is an ascending order. And let's say that you are looking for a value of 32, okay? We are looking for a value of 32. So what we do, we check the items one by one, starting from the head. 17 is less than 32, so I should go on. 26 less than 32, I should go on. 31, go on. But now if I come to that point, I see that this is 54, which is higher than 32, and since I already visited the previous value, I can conclude that we don't have any 32 in this list, and I don't need to check the upcoming, let's say, values. So this is a nice way of actually searching in the ordered list. Things are much simpler. You don't need to spend time on checking all the items. This is actually what I mentioned, summarized here. If the current value is higher than the item you are looking for, you should stop right at this point and return this found variable if you have found it or not. So how we do the adds? If you are going to add an, let's say, item into your list, then you should be very careful. Since this is an ordered list, yes, you have 1, 5, 7, 9. So assume that you have 4 values in your ordered list and in your ascending order list. And if you have a new item, which is, let's say, 6, and what you need to do, you should find an appropriate position here. So you need to find that position and put it here. So this is the important part for the adding items into this ordered list. So this is how it is done. If you find the position, the index where your item should be, then you should have new connections between the previous and the next items. So as you see, initially 26 was connected to 54, but after the addition of 31, it should be connected to 31, and 31 should be connected to 54. Initially, once you create a node, we have an ground value as a reference, but since once you add it into the list, it will be an intermediate item. You should also modify the reference value of this node. This is actually the implementation. We have similar operations like search. We do search operation, find the appropriate position, and then modify the references. This is done here, but not that complicated. So let's summarize what we have learned in this chapter. We discussed linear data structures, the queues, stacks, decks, and the list data structures. They're all linear. We can add some items into them, remove them, have some operations. And we said that the stacks are last in first out type of data structures. In some specific problems, they are highly useful. It makes your actually job easier. We have adding items operations, pop operations, not many operations, but still is very useful data structure. Then we discussed the queues, and we said that it's mostly used in simulation type of operations, task problems. And it's an first in, first out type of data structure. The item you put first will be popped out first, which is not the same, not the case in stack data structure. And in stack, you pop actually the item you just put. So that's why it's last in, first out data structure. And in the queue, we had similar operations, generation of the queue, adding items like enqueue or removing items with the queue. And once you run the dequeue, it will remove the oldest item in the data structure. Then we discussed some examples about prefix, infix, and postfix illustrations of mathematical expressions. And we discussed an implementation for infix to postfix conversion. And we use a stack data structure while doing this conversion and while actually evaluating these values. And the stacks can also be used for reversal. Since it's a last in, first out type, if you run it twice, and you will be reversing your values. And I mentioned that the queues are highly useful for simulations. So you can check what happens if you have such an, let's say, property with your printer, with another machine, another system. You change the variables and see the output, and in these simulations, you can easily use the queues. And we said that decks are another type of linear data structures, and it's a kind of hybrid data structure of stacks and queues. You have almost no restriction in terms of adding and removing items. You can perform these operations at the front or at the rear of the data structure. Then we discussed the list, as you remember, unordered list and ordered list. Depending again on your problem, you may have any of them. And in the ordered ones, we spent less time on finding specific items. And in most of these operations related to lists, we need to do some modifications at the heads, in the references. By playing with them, we can easily perform many operations on the unordered list and the ordered list.